I'm continuing the lectures on chapter 4, that is Introduction to Convection, with a discussion on the Ban-Rayleigh equations. These provides a theoretical background that is particularly useful at explaining correlations. And correlations are essentially the equations that are used in order to calculate quantities of interest to us engineers. That is, you can estimate the coefficient of friction, the convection coefficient through the Nusselt number by just knowing one quantity, that is the non-dimensional Reynolds number and Prandtl number, just to name one example. So these correlations are essentially what we will be primarily working with in this course, but what we're doing now is explaining why they can be written in such a way. That is why you can say that the coefficient of friction is only a function of the Reynolds number. And one convenient way of doing that is working with the governing equations. You start with a full set of Navier-Stokes equations, which you simplify on the basis of certain assumptions. These assumptions are reasonable for the type of surfaces that we're interested in, that is flat surfaces or lightly curved surfaces. And it makes for equations in the end that are amenable to reasonably easy manipulation. So what is a Ban-Rayleigh equation? It's the governing equations for flow over a lightly or slightly curved surface. And what is slightly curved surface? It's a general concept, or it's a reasonably loose concept, but it's an important one. If you are looking at what you see in front of you there, you can easily guess, I think, that this dashed line represents the path taken by the particle on average. Perhaps it's turbulent and fluctuates about it, but by and large, the particle follows reasonably well the contour of the surface. If you had a very rapid change in the shape, perhaps if it was to drop suddenly and create a step of this nature, then the flow is quite likely not going to be able to follow the contour unless it's extremely slow or unless you have perhaps a very low Reynolds number. If not, you will get what is called Ban-Rayleigh separation. The flow will detach from the surface, and in an attempt to reconnect with it will create large vortices that are very unstable, that is, they change over time and space, and that means you can't really simplify the governing equations in any way. All three components of velocity as well as time need to be resolved, and that means that you're dealing with a very complex problem. However, if you assume that the flow follows the contour of the surface, you can make certain simplification. The first one requires a little bit of an explanation of what x and y is. It's a two-dimensional coordinate system. That is, we only resolve what's in the plane of the screen. Here, we assume it's a two-dimensional problem. And directions are chosen to first follow the contour of the surface. That is, direction x, which is also called the streamwise direction, is locally the direction of the surface of the fluid that flows along the surface. So if you move along the surface and you position yourself here, the direction x is going up. Whereas if you position yourself here, it's almost horizontal. That means the coordinate system changes over space. The direction y is the wall normal direction. So also this one will change as you move along the surface. What you have to remember now, for the Ban-Rayleigh equations, you can assume that the flow is only in the x direction. So the flow in the x direction is represented in terms of the velocity vector. The velocity vector has two components, one in the x direction, one in the y direction. If the fluid flows only in the x direction, then it means that the v component of velocity is 0. And the velocity is all in the x direction, so it means the only component that matters is the component u. In other words, it means that the flow is parallel to the surface at any point. So if you look at yourself here, the flow is parallel here, here it's parallel to the surface. The velocity profile in red shows that the velocity u varies quite a bit in the y direction. You've got a significant gradient in u as you move away from the surface. But in fact, there is very little change as you move along the x direction. That is, the velocity u will be almost the same, perhaps at this point, compared to this point here. So du over dx is close to 0, whereas du over dy will be significant. I've picked u as an example, but I could have said the same thing for c and t. That is, all flow variables vary primarily in the y direction and not so much in the x direction. That's one of the fundamental assumptions of Ban-Rayleigh flow. So d over dx is much larger than d over dy. The other one is that v is equal to 0, while u is much larger than v, if you prefer. Other assumptions that are made here to simplify the governing equation is that the flow is incompressible, that is, the density is constant, and we can represent enthalpy in terms of temperature. The other flow properties are also assumed constant. We neglect the effect of body force, assuming that the inertia of fluid is much stronger than what the gravity does. We neglect energy generation within the energy equation. We assume the flow to be steady, that is, there is no dependence with respect to the time variable, or in other words, d over dt is equal to 0. The flow is non-reacting, that is, you don't have a source of species or any of the species when you're looking at concentration conservation. So let's move on to the full set of two-dimensional governing equations based on that correspond to these assumptions. That is, for example, we said that density and mu were constant, so you don't see them appearing within the derivatives. We have the continuity equation, the x momentum conservation, the y momentum conservation, the energy equation, and the concentration conservation equation. This term here refers to the viscous heating, whereas we've got a diffusion of heat here, and we've got convective transport of heat there. So that's the same for all of these equations. The left-hand side corresponds to convective transfer. We have a diffusive process, and we've got a source term due to the pressure gradients here for momentum, whereas for concentration, we have again a convection transport and diffusive transport on the right-hand side. So if you see the second derivative of the conserved quantity, it means you're dealing with a diffusive process. Diffusion, diffusion, diffusion. If you see the velocity linked to a gradient in the conserved property or variable, then it means we're dealing with the convective transport. So convection, convection, and convection. And this is mass conservation. Okay, so that's just a review, a very rapid review of things we would have discussed previously. The next slide looks at how we can incorporate the simplification we discussed previously into the equation so that we derive simpler form of equations. So two of the terms two of the simplification mentioned here are written in mathematical form. That is, flow variables do not change much in the x direction compared to the changes in the y direction. So what matters here is how large one term is compared to another one in a given equation. So if you see any of the equations, you have several terms added to each other on the right and the left-hand side. You can remove one term if it is much smaller than the other one next to it or on the other side of the equation. So if this one is much smaller than this one, then you can neglect this influence. Let's do that with the very first continuity equation. We would have to compare d over dx and dv over dy. d over dx means using a derivative with respect to x. We know this is very small compared to derivative with respect to y, but we look at the derivative of the x component of velocity. The x component of velocity is much larger than the y component of velocity. We said that v was almost 0. I said 0 early on, but in fact we're going to say that it's much smaller than u. It is not strictly equal to 0. If we go back to the sketch representation, the reason why these lines diverges, if they were virtual boundaries of the flow, or if they were path line followed by the particles, they diverge a little bit simply because the flow does move away from the surface here a little bit. That means there is some element of a y component to velocity, even though it's small. So we look at the relative importance of these two. So when we compare these two together, we see that they combine one that's small with one that's large with one that's small. Okay, so they are both actually of similar order of magnitude, and one cannot be ignored when they are present next to each other in the equation. So neither of these can be simplified. Continuity equation remains as is. So let's move on to the other equation. Now, we're looking here at the x components of the momentum equation. We do recognize that this one has to be much smaller than this one. We look at the derivative with respect to x. We know that derivative with respect to x give a value that's much smaller than with respect to y. But again, it's put next to a term u, which is much bigger than the one that the other term is added to. So if you compare these two, this is larger than this one, and this one is smaller than this one. So both are of similar order of magnitude. They cannot be simplified. Whereas on the right-hand side, it's not the same story. d over dx is much smaller than d over dy, and it's the same for a second derivative. So this one is much smaller than this one, so we can ignore this term. And that's what's written here. All this is approximately equal to that. We simplify the equation in that way. The only thing that has changed from this equation compared to this one is this term here has been removed. Okay. Next, the y component of momentum equation. We go back to a sketch of our boundary layer flow, and we consider the two equations side by side. Okay, so let's look at the pressure term. Okay, what does create a pressure gradient, by the way? If you have a flat surface, completely flat, rather than this curved surface, we know that's called an external flow over a flat surface, and we know it will create no pressure gradient, and that can be proven. I won't discuss it too much, but what we know is that outside of the boundary layer, the pressure here is going to be the same as what you find at anywhere along the y direction. So how do we know that? Okay, so if you look at this, you rearrange that equation so that you put the pressure gradient on the left-hand side. You bring that there, so therefore you bring this term here to the right-hand side, and you keep this one to the right-hand side. That's what that gives. That's where this comes from. Do the same with the other equation. And then we look at the various terms. Are they smaller or bigger? We know that this term, u, okay, so v and x, that's very small. Okay, this one, oops, sorry, this v and v is very small. This v is very small, very small. In fact, all of these terms are very small compared to all these terms. So now I'm not comparing them side by side, but top to bottom. All these are going to be much bigger than these because v is very, very small. So we look at changes in v, but we also multiply by v, so they are all very, very small. And that's what that statement is. And you do the same with these derivatives. The gradients of the velocity v are much smaller than the gradients of velocity u. In particular, this one is the dominant one compared to all of the others. And this one would be the dominant one compared, sorry, these two are bigger. I'm not going to go into the details because you see here that this is small and this is large and this is small. This is small and this is large. But in combined, if you were looking at this is small and this is small, and this one are also small. So all I'm saying here, and all you have to remember, is that all of these terms are much bigger than all of these terms. And that's what that gives us, that particular equation. We know that the pressure gradients in the y direction is going to be much smaller than the pressure gradient in the x direction. It's the opposite to what we've discussed before. That is, gradient in x were smaller than gradient in y. For pressure, it's the opposite. We can in fact assume that pressure is not a function of y in the boundary layer. So it means that if you were to slice the boundary layer with a line and you were to follow the pressure anywhere through it, you would find that the pressure is almost the same as the pressure outside. So it means that really the only thing that varies in terms of pressure is the pressure outside of the boundary layer as you go along the x direction. The curvature creates a pressure gradient in the x direction. It creates high pressure at the forward stagnation point and a gradual decrease when you have a curvature like this one. We can use Bernoulli equation to explain that, but what's important is that the pressure in the section crossing the boundary layer will be the same as on the outside, and you've got most of the pressure gradient appearing out there. If you've got a flat surface, that term is zero. When it's slightly curved, you end up with a pressure gradient that is significant. So that's how these equations are used. You basically remove this one to zero. In fact, all of these are zero for the y conservation momentum equation, but these terms are not zero for the x conservation. Okay, so we leave the momentum conservation equation aside and we move our attention to the thermal boundary layer now. And in fact, the simplifications are very similar. So what are they? It's a little bit more complicated than some of the others because we've got something called a viscous heating term. And the viscous heating term is essentially a transfer of mechanical energy to thermal energy through viscous dissipation. So if you rub two fluids together very intensely, you generate heat in there, and that heat is transferred into a generation of heat. So looking at the overall energy conservation equation, we have the convective transport, the diffusive transport, and the heat dissipation. How can these be simplified? We can see that this one is much smaller than this one, but this one is much bigger than this one. So the combination means that both terms are actually of similar magnitude. We can't simplify. But when it comes to the diffusive term, the derivative with respect to y is going to be much larger than derivative with respect to x. So this term can be simplified and left out of the equation. You see it's gone from here. For the other ones, we know that d over dx is very small. dv over dy, even though there is a gradient in the y direction, v is very small, so this one is also very small, whereas d over dy is large, whereas dv over dx is small. So all of these can be simplified using what's in red there. You're just left with this one here, and it's squared, so that's why you have the square. Okay, so this is the viscous heating term, viscous dissipation, or viscous heat dissipation term, sorry. And this term will actually be ignored in the remainder of our discussion because it's very often quite small. There's one non-dimensional number that can be used to assess whether it is important or not, and let's assume that for the problems that we're interested in, it is negligible. So it gives us an equation that's quite simple. The concentration boundary layer is essentially a lot like the thermal boundary layer equation, except there is no dissipation term as the one we discussed, but the others are the same assumptions. That is, convection can't be cancelled out, can't be neglected. And the primary diffusion term is the one that is involving the derivative with respect to y. The coefficient in that case is the diffusivity coefficient, whereas in the previous one was the conduction coefficient of the fluid. But other than that, it's very similar. If you combine all these simplifications, you end up with this set of boundary layer equations, which is simple. But most interesting is the similarity in the shape of the three last equations. Momentum, remember only the x momentum remains, and it's important because we assume v to be actually quite small, so the v terms disappear. We could have said it that simply. V is not going to be resolved. We assume it's very, very small. Therefore, the equation is not important. I didn't actually, and I should have replaced the dp over dx. This is not incorrect, but we know that we wrote it as dp infinite over dx. Okay, so that term there can be used to replace this one, but this is correct as well. If you forget this pressure term, then you will see that you have convection, diffusion, convection, diffusion, convection, diffusion. So the same shape. The only changes are these coefficients that are a little bit different. And that is important. We've, by the way, neglected viscous heating, as I said in the previous slide. So these are the governing equations. The next step is to transform those governing equations in what are called non-dimensionalized or non-dimensional governing equation. It looks like a lot of complication or added layer of complication that perhaps is not necessary, but it brings one more layer of sophistication that makes the similarity between the equations even more obvious. So how do you do that? You define non-dimensional form of each of the variables. So the easiest one perhaps is x star is the non-dimensional form of x being the position along the surface in the streamwise direction. And the way we non-dimensionalize, we divide x by a characteristic length. That could be the length of our curved surface, for example. Use the same non-dimensionalization for the other coordinates in space. And for the velocity, you divide by a characteristic velocity. We don't have to decide what it is, but more than likely you're going to say, going back to here, is the free stream velocity, the upcoming of the velocity that's upstream of our object. So we've got our non-dimensional form of each one of these equations. You could rewrite now u as being u star multiplied by capital V, for example. So if you take that alternative definition of u and substitute it in each one of these equations, for example, the conservation of mass equation, that is, you replace u by u star v, you put u star v here, you put v star v here, as done here. We also account for the chain rule of differentiation. D over dx star multiplied by dx star over dx gives us the same as the d over dx. Okay, so that's just a mathematical rule. If you apply that, dx star over dx would be d over dx of this quantity. It would be 1 over L, and that's how we end up with 1 over L here. The v comes from taking the v out of the derivative, and you have it there. So now we can simply divide throughout that equation by V over L, and that gives us the non-dimensional form. You can repeat the same with those, each one of these governing equations. And what's interesting is on the right-hand side, we see that we end up with a non-dimensional number there, which is the inverse of the Reynolds number. This one is the inverse of the Reynolds number by the Prandtl number, and this one is the inverse of the Reynolds number by the Schmidt number. Each one is redefined there in terms of the characteristic length, which can be defined as you wish depending on the problem, and we discussed them on the previous slide. Boundary conditions are expressed in non-dimensional form. It's easy enough to see that at the edge of the boundary layer, U star is going to be equal to U infinite divided by V, and so on. So these are very simple. But the bottom line is that perhaps we can solve it, but that's not going to be our interest. From there, we can see that, for example, U star is going to be a function of the Reynolds number and the pressure gradient. Okay. Temperature is going to be a function of the Reynolds number and the Prandtl number. The coefficient or the concentration CA is going to be a function of Reynolds number and the Schmidt number, as well, obviously, position and velocity, and so on. Okay, so how do we write that? That's the next step in our discussion. The non-dimensional boundary layer is going to be exploited in order to explain the functional description of quantities, and I'm going to leave that to a second recording rather than continuing to a single one.